everybody, and we're finally back with another roundtable. I know it's been a while, guys. What can I say? We're finding it difficult to actually get people to come and do presentations, although Brian has stepped up to the plate yet again. I think this will be his either third or his fourth presentation. So we're on number 27 now, and this is AngularSize change, visual occultation, and the diffraction limits by Brian's logic. So I'll give him a call in just a second and he should be ready to roll. But what I would like to show you guys is, just bear with me, let's go to this here, and I'm going to promote a channel here. So this is a channel called Sky Free. Let me copy this, and what I'm going to do is I'm going to paste the link in the side chat. The channel is awesome, I have to say. The channel is amazing. Does some incredibly good miniature scale observations across a rather small pond/lake. I think it's only about 600 feet across. So highly recommend going across there. It might help you understand the observations that we've been talking about these past few years, and very worthwhile subscribing over there. So I'm going to post that link in right now, so please guys go and subscribe if you would, and click that bell notification as well. At the end of the day, you know, we only survive here by having people providing content. So Skyfree is a new content creator. Let's support them as best we can. So a few shout outs. We've got Cleary in, Nathan Oakley, nice to see you in. Nathan, I'm glad that you put your show back till midnight, I believe. Excellent, thank you very much. So that gives us an hour and a half or so with Brian. Ian Matheson, nice to see you in. Domesticated Primate, thank you very much. Thanks for your emails as well, I appreciate them. Lots of people in tonight. Right, let's see if I can get Brian on the call. I'll just give him a bell right now, so just bear with me. Hello.
Hey, how are things?
Hey, glad to see. Glad that I finally got a hold of you. I was sort of worried then that we might not have a show because I couldn't get a hold of you.
Yeah, sorry. It always happens just before I go online that I'm needed to do 3 or 4 different things that only I can help out with, you know, that kind of way. Just before I came on, these things happened. It's just every time I'm about to come online, there's always like a load of stuff that has to happen just before it. If it wasn't coming online, it wouldn't happen, you know, that kind of a thing. It's just the way it is. So I was just washing my hands literally when you rang me. So I couldn't get to the computer and kind of be there on time. So I apologise for that.
I'd just like to give a massive shout out to Nathan Oakley for the £1.99 super chat that says, "Give Ranty money!" ! I'm not going to say don't do that. I'm incredibly poor after having not any working for the last couple of months. So yeah, anything you can do that would be a bonus. So that's my little shill moment for this evening. But in the meantime, we do go on. So you were going to say something, Ryan?
Just support Randy. That's what I'm saying.
But more importantly, support people that go and find the truth and look for answers and reasons and try and help this this unraveling of the global eye. So we have roundtable 27. This is AngularSize change, visual occultation, and the diffraction limit. And this is your presentation. I know you've been working on it for quite a while, so I'm hoping that you've got plenty of good stuff for us.
Yeah, it's I finished a couple of months ago, but I just never got around to with coming close to Christmas and then Christmas time. Just never got around to doing it. Just things got in the way. But at the start of it will be a bit of reading, and then it'll be all visual from there. Okay. Basically, all visual from there. So well, I'm after putting. I'll have to skip over some parts because I want to make it within less than an hour, so I'll have to skip over some of the less important parts, but they'll be there in the thing for anyone who wants to see it and look at it anyway.
Yeah, that's perfect. If we can get done for around about 20 to 12, and then I can take a few questions from the audience, that would be great, because I know Nathan's put his show back till midnight, so if you've got an hour to do this, do you think you can do it?
Oh yeah, well, I'll be watching the time, I'll do it within
Excellent.
I'll make a point. yeah, for sure.
Okay, right, Brian. Whenever you're ready, mate. I've got you on screen. All you have to do is share your screen, and we'll crack on. I'll put myself on mute, and we'll get started.
Okay, 1 second now. Share the screen. Let's see, where am I going? I'm doing something wrong here. Oh, there I am. What am I doing? Sorry about that, I was pressing on the wrong thing.
No worries. Shout out to Flat Enough and Bible Literist in the chat as well. Nice to see you in. Ian Adams, nice to see you in as well.
I should be sharing now, Randy?
Yep, you're sharing your Skype at the moment, so if you want to present something else, that would be...
I'll do. Okay, I'll get started on it then.
Excellent, away you go.
Yeah. Okay, on the ball. I'll keep it on time, and you let me know if you feel things are running on a bit.
Okay,
I'll keep an eye on it, Randy.
No problem, I'll be on it. Right, speak to you in a bit.
Talk to you in a while. Okay. Okay, I'll start. There's going to be a bit of reading.
Just one last thing. Can you click that X off in the top right? Yeah, just get rid of that box.
Yeah, there you go.
Yeah. No, top right. Or is it me? No, it's you.
Mine on the screen anyway.
Okay, right, fire away.
Yeah, I'm just seeing the presentation and whatever stuff is going on down at the bottom there. Just everything okay?
Yeah, good to go.
Okay, on the ball. Okay, angular size change. Okay, I'm going to have a bit of reading at the start of it, and then it's going to be visual from then on in. And try and chop it down as much as possible. Okay, on the globe side of this argument, the angular size change of an object in an observation made by someone on either side of this argument is ignored, as in it's never taken into account in calculations and investigations of people's observations. Even surveyors in general don't take angular size change into question. They know what it is, but it never enters their final calculations, as if the surveyor sees something at a distance that is also at an equal elevation as to where they are, but this observation is actually dropped in their field of view, even if it's a small distance of a few miles, the surveyor will just presume it to be the drop of a curved earth, as that's what he or she has been taught to expect their whole lives. Something that Samuel Rowbottom did to prove his point during the Bedford Levels test of flat or curved was that he noticed that when he aligned the crosshairs of his telescope up with the first marker, that the other marker seemed to fall away from view in the background. But the most pertinent word in that is the word seemed, as Rowbottom knew that it was what is known as angular size change, but he needed a way to prove this for his claim of a flat earth to be taken seriously by his subtractors. So what Rowbottom did was he determined that if he aligned his telescope up with the first two markers, that if after that the following markers in the background still fell below his telescope crosshairs, then the earth was curved and a possible globe. But if the crosshairs aligned with all the markers in a line, then this proved three things. One, the angular size change was a real and provable thing and a very important part of any observation at distance. And two, that the Earth is a flat plane, as his observations and methods did not correspond with the official calculations of what he was told to expect when making these observations. And three, that water did not curve as people expect to see happening in any way, shape or form as the water level, through the 6 mile stretch of the Bedford Canal stayed uniform without deviation. Surveyors and engineers. Once again, I must speak about surveyors, as when taking measurements, most surveyors for construction purposes will only use their theodolites to predict about 300 feet into the distance, as after this distance, theodolites are less accurate, supposedly. Now, this is not a theodolite problem, as it's an atmosphere and perspective distance problem, which causes irregular measurements. It's not that the theodolite cannot view further, as it's a form of telescope, so it obviously can. What happens is the surveyor knows that working inside smaller distances from point A to point B to point C, etc., will give a more accurate measurement. Now, surveyors may not always work within this 300-foot range, and I'm sure it's dependent on what they are surveying and for what reason the surveying is taking place. But if they want accuracies in their work, they have to adhere to using smaller distances for this. So what happens when the surveyor believes they have made an observation at a distance of several miles and the crosshairs of their theodolite is above an object or piece of land that is believed to be at the same elevation as where they stand? Well, basically, they presume that it's the curve of the Earth and carry on with their observation while making calculation changes and allowances for this suspected curve. When their observations are put into practice by an engineer, he or she just works with making things level, and it all seems to work out whether they are building a bridge, highway or a hospital, etc. This is why people on the opposing side of this argument believe that level means curved, as that level means to be following the supposed curve of a globe surface, and that all elevation calculations are starting off at the center of an as yet unproven sphere. So this makes everything level makes everything level, as with large distances it supposedly would not be noticeable. But going off the official curvature calculations of the globe belief, these differences over distance would be very noticeable and severe. What surveyors are not taking into account is the fact that an object's angular size has changed with distance. So even though it's below their theodolite's crosshairs, that does not mean that it went over a curve, just that it's gotten smaller with distance compression due to perspective. This is not a difficult concept to understand, but still the opposition of this argument fail to see this, or in some cases just plainly deny that this is happening, while they see ample evidence of it every day all around them. What is happening on the smaller scale in our field of vision is also happening on the bigger scale too. So when someone sees a car in the distance that was bigger than them only 20 seconds previous become the size of a toy in their perspective vision only 20 seconds later, that's angular size change. So when we see a large object at a great distance that appears to have shrunk, that is because from a frontal view it has changed in angular size. Not that it really has shrunk, it's just an effect of perspective. Now what has happened is the opposition in this argument will show the same observation from a side-on perspective, also known as orthographic view. And in this view the object has appeared to, in this view the object that appeared to have shrunk in the distance will show a much more actual size. What normally happens is the people on the opposing side of this argument will take an observation and proceed to measure foreground objects off of background objects, and the foreground objects are in actual size smaller than the background object they are being measured off. But in frontal view, in a photograph or video, due to distance, the foreground object appears to be larger than the background object, when in actuality it is the opposite. Following on from this, the opposition will show a 3D model of the same observation that was seen in frontal view, but their 3D model will be in side-on orthographic view. And in the side-on orthographic view, there won't be the same angular size change between the previous foreground and background objects, as they will now be to the left and right of the observation as opposed to front-on. So it will then be claimed that due to the differences in these two differing angles of observation, that the background object is smaller due to going over the supposed curve of the Earth. But this is totally debunked due to angular size change. Diffraction limit / occultation photography. The diffraction limit is an effect that happens to all optics, whether they be natural like your eyes or man-made like telescopes and cameras, etc. The diffraction limit happens when the angle of view to an object in the distance becomes too tight for your optics to decipher the bottom of the said object apart from the ground it sits on. Or if the object is in the air, then its angular size due to distance has caused it to be non-decipherable. This is the diffraction limit. When big objects obviously with big objects, the distance will have to be more to create the diffraction limit than with a smaller object. For instance, a boat of 16 foot in length sitting on calm water with good clear weather conditions several miles out from shore will start to disappear bottom up when viewed from a 5.5 to 6 foot viewer height from the water's edge, as the angle of view is decreasing the further the boat moves from shore. Now, with a ship of 100 feet in length and 70 to 80 feet in height, we'll have to obviously have to move further away than a 16-foot boat to enter into the realm of the diffraction limit. Now, the same is true for any dry land, where a camera placed close to the floor or ground will show the diffraction limit pretty fast, as long as there is flat and level ground unobstructed. As anything moving away from that camera will eventually begin to disappear from the bottom up, as the angle of view will rapidly be decreasing due to angular size change. Now, this effect is hard to capture with big buildings, as big buildings are nearly always in a place where there is a lot of obstruction of view, as you move further away from the big building and create distance from it, it will begin to shrink in height, and buildings in your foreground that are not as high as your chosen building in the background will begin to occult it. This is what is known as photographic or view occultation. What needs to be remembered about the diffraction limit is that it is dependent on a couple of things when you will notice it. One, it depends on the size of the object you're viewing and how far away from it you can be, or it from you, in an unimpeded field of view. Two, it depends on weather conditions also. If you have good weather conditions, you will have greater clarity at a distance than without good weather conditions, obviously. As it's good to remember that the diffraction limit is connected to lighting, clarity and optics. And a good example of this is the horizon. As the closer you are to the ground, the faster the horizon will appear to occur. But the horizon distance is also dependent on weather conditions. As with good conditions, you will see an horizon further than with bad conditions. Three, the biggest changing factor overall, though, concerning the diffraction limit is the optics being used. As with our own natural optics or eyes, there is going to be differences between people, as one person could have a greater penchant for distance viewing than someone else, and that would mean that in a general sense the diffraction limit will happen a little later for that person as opposed to a nearsighted person. Hence, my diffraction limit may be different from yours. And the same applies to cameras and telescopes, etc. As a camera with a greater distance zoom will have a greater diffraction limit than a camera with a lesser zoom. Even if the lesser zoom camera is technically a better camera for general photography, and the same applies to other optics like telescopes. Please remember the diffraction limit is an effect, a natural effect, not a man-made one. A lot of the time, the diffraction limit is connected to what's known as the Rayleigh criterion. The Rayleigh criterion is an hypothesis basically that says that when an object becomes too small for your optics to decipher, it will start to amalgamate within itself and with its surroundings. This Rayleigh criterion was originally detailed by people who use microscopes, as it's a very common thing when looking at things on a micro level. This is widely detailed by laboratory scientists and opticians. I'm not going to read this out. This is about the Rayleigh criterion. So in case anyone wants to know about it, this will tell you about it and show you about it. Just talking about two light sources amalgamating into one in your vision, even though they're not the one. There's about 20/20 vision, which is part of the diffraction limit is obviously going to be part of. And this is an eye chart that we all know of. And this is when it gets the letters and numbers, whatever gets smaller, that's when it goes into the diffraction limit. That's when you can't read it anymore, because it's got to get into a point where it's just not decipherable. Okay, this is just an everyday. We all know this. We've all seen this. Almost every classroom will have something like this in it. Even absolutely every doctors and opticians will have it. As you're growing up. So we've all seen that. But that's a good example of the diffraction limit when you can't read the very bottom or close to the bottom letters and numbers, because you're just not able to decipher them. That's about the size of it. Now, what should be remembered is that although the Rayleigh criterion deals with stuff on a small scale, the diffraction limit does not have a size limit, only an optical limit. This means that anything can reach the diffraction limit of your optics, regardless of your size, as the diffraction limit is dependent on quality of vision and zoom abilities, not object size. The sunset is a great example of this, as on the flat out side of this argument, the opposition constantly asked the question, how could the sun set if the earth was flat? Now, what is really happening with most sunsets is not that the sun itself has gotten a great deal smaller in our field of view while setting as opposed to when it is at noon. It's that our limit of vision is less than the distance the sun is making from us. This is why with normal vision standing on a beach looking out at the horizon, the sun will appear to disappear below it, but this is not what is happening. You see, the horizon is a diffraction limit, the point at which your eyes and our optics cannot reach beyond. But this does not mean that the sun has disappeared. It's just that it leaves your vision distance. It's just that as it leaves your vision distance, it appears to disappear from the bottom up. It's still there, but it's moving away from you so fast that you're losing ground on it visually. It's reached your visual limit, and this limit starts from the bottom up. On top of this, what must be remembered is that even with the best zoom cameras or telescope, you still will not be able to track the sun for very long, as it will reach the diffraction limit of your optics regardless of their abilities, as you're very small and stationary and the sun is very big and moving. Basically what I'm saying there, I'll keep reading on. Actually, people will assert that the sun is not changing in angular size during its daytime, but this is not true. It does change its angular size, but only by a small amount. That's not very noticeable. That's not very noticeable. I don't know. I don't know what the sun is, but I know that it's moving fast. But it is also very big. So big, in fact, that I hypothesize that we don't have optics good enough to follow it. So it will reach our diffraction limit before it's far enough away to make any real noticeable angular size change. Basically what I'm saying there is that the sun basically goes so far away from you that before it makes any real angular size change, it's because it's so big, it starts reaching your diffraction limit before its angular size change has actually really noticeably started. Like it is changing angular size, but it's only because it's so big, it's hard, you're not deciphering it, basically is what that means. Right? If you imagine Mount Everest floating away from you in the sky, it would start, the bottom of that would start reaching the diffraction limit before that starts starting to look like it's getting very small. And like, we don't know how big the sun is, but we know it's a big object. So if you can imagine Mount Everest floating away from you in the sky, and the bottom of it will start hitting the horizon, which is wherever your horizon is, whatever optics you have, it'll start hitting that horizon, which is your diffraction limit, and it'll start disappearing from the bottom up. But it's not disappearing, it's not actually going over anything, it's just going so far away that the diffraction limit is happening before any real noticeable angular size change is happening. And that's what happens with the sun. The diffraction limit starts before the angular it's not in reality starting before angular size change. It's that the angular size change is happening, but because it's so big, it's not so noticeable. So it goes into your diffraction limit before it actually reaches any really noticeable angular size change. It will only change by a very small amount before it reaches the diffraction limit of our optics, and at the time it starts to disappear at the horizon in accordance with our optics, it's already too late to see noticeable angular size change of it, as we just can't follow it with zoom, as we have used all that. As we have used all that up, by the time you see the sun at the horizon, it's over. What is occultation? Occultation in photography is when the object you're trying to photograph is being obstructed by another object that is not quite as high as your chosen object, but is higher than the camera height. So consequently, you are forced to aim your camera lens upwards to take the shot. So, a good example of this is when there is a photograph taken from a good distance away, and the largest object in the photo seemingly has shrunk into the ground, as most of your photograph is taken up by the foreground object that is higher than you, but not nearly as high as the object it is occulting. Mostly this happens to its extremes when there is a fairly large distance between you and the occulting object, and the occulting object and target distance, and target object. Some good examples of this is when a photographer is taking a photo across water and there is a ship or large boat at a distance. It seems to be half sunk into the water, or basically the photographer can only see the top half of it, of it, as the bottom has been occulted by the rolling tide and swell. So basically what that means is that you could have a boat that's pretty big out at a distance, but because the tide and swell, because its angular size is bigger or big enough to block out half the boat, it seems as if the boat is going behind the curve, but it's not. It's down to angular size. The boat or ship has gotten so small that the swell that you're looking at before, that's in your foreground, is actually the swell you're looking at that's in your foreground is blocking the half of the boat or ship. And as that's all that's happening, the angular size of the swell is bigger than the boat. That's basically, or bigger, or as big as half the boat, and that's what's happening. And as the further boat goes away, the smaller its angular size gets in relation to the swell. Some good examples of this is when a photographer has taken a photo across water and there is a ship or large boat at a distance and it seems to be half sunk into the water, or basically the photographer can only see the top half of it as the bottom has been occulted by the rolling tide and swell. As if there is a constant swell in a tide, which often is the case due to underwater topography and weather conditions, that what will happen is between the observer and the ship there will be a sea swell, and even though this swell of the ocean won't actually be bigger than the ship, its angular size at its given distance will be half or more of the size of the ship. So consequently, in the camera's field of view, it will occult the ship or boat as the swell is in the foreground of your observation and the ship or boat is in the background. So it's going to have the amount blocked from the view in direct correlation with the angular size of it in comparison to the angular size of the swell in relation to the swell's distance from your camera. Now, because it is the ocean that we are talking about, it must be remembered that there can be other factors at play as to why something is blocked from clear view, as there are several differing effects due to weather and other factors that can cause visual blockage at sea. Another good example of occultation is when there is a photograph taken of a high mountain or building, and that mountain or building is surrounded by other smaller objects of less height, but they are in the way of a photographer's line of sight to the larger mountain or building, and the photographer is either less close to these observations, obstructions, or very far from them, then occultation will take place. Angular size change equals an object's apparent, not actual size, due to distance compression and atmosphere. The diffraction limit is the point when an object's angular size change due to distance has rendered the object undecipherable from its surroundings in accordance with the optics that the object is being viewed with. Occultation is visual blockage in a photograph or observation due to a foreground object's angular size in comparison to / with a background object's angular size change, causing a blockage in view. Okay, this is just like perspective. This dog is not bigger than the house, obviously. It's just perspective, right? He's in the foreground, right? If that house was to the right, then he would totally block out the house. Okay, so if you can imagine it like that, if the house was over here, right, we'd only see the roof of the house, because he's occulting it. That's a good example of it. I know it's a silly photo, but it does the job. Now, onto Mount San Jacinto, right? This is a great example of occultation and angular size change, okay? This photograph from J. Tolan of Mount San Jacinto from over 123 miles away is an absolutely fantastic example of angular size change and photographic occultation, as it displays both very beautifully. This photo was taken from 150-foot elevation and 5.5 foot camera height at Malibu's Point Dume, north of the city of Los Angeles, California. It is from 123 plus miles away from Mount San Jacinto in the San Jacinto mountain range, Southern California. In the photograph above, we have distance compression causing angular size change. So distance compression causing angular size change as Mount San Jacinto would tower over Los Angeles and the photographer if it was close to both. But because it is so far away, it's changed in visual size as it's actually over 10,000 feet high. Also in the foreground of this photo, there is the city of Los Angeles, which occults the photographer by 100 foot in height. So that when Jay Tolan was taking his observation here of Mount San Jacinto. Mount San Jacinto is about 124, I think it is, miles away from him. Right, he has 123 down here, but I've seen it at 127 and blah blah blah. I worked it out at about 124, but it doesn't matter because I'm going to show something later that will cause that will throw a spanner in the works. So basically, if you were to drive to Mount San Jacinto from Point Dume in Malibu, and you drove at 60 miles an hour for 2 hours solid, that's the length of time it would take you. You still would be several miles away from, you still be a couple of miles away from Mount San Jacinto. So to go that distance, you'd have to travel for 2 hours straight, unimpeded, at 60 miles an hour from where Jay Tolan is to Mount San Jacinto. So that's quite a distance. If you can imagine a 2 hour drive at 60 miles an hour, non-stop, no stopping, no obstructions. That's how far away Jay Tolan was from Mount San Jacinto. So he's basically a 2 hour drive away from it. That's how far away from it he is. And Los Angeles, in his view, cuts him by 100 foot. So he's 150 foot observer height. Los Angeles is 250 foot he's 150 foot above the sea level, and Los Angeles is occulting his view by, it's 250 foot. So it's occulting him by 100 foot over his height, over his camera height. So that's 100 foot over. So so some little detail here, right? Mount San Jacinto height is 3,302 meters, right? 10,833.33 feet. Photographer's elevation 150 feet, camera height 155.5 feet altogether. Google distance from Point Dume, Malibu to Mount San Jacinto is 155.5 statute miles. This is what Google gives us, or 135.217 nautical miles. Google Maps calculation of distance is actually 244.59 miles. So Google Maps actually calculates the distance at 244 miles. And I'm going to show this in a while. Generally accepted distance 123 to 125 miles. Geometric drop for 124 miles at 155 foot viewer height on a globe would be 1.94 miles. Okay, that's the drop. Geometric hidden for 124 miles at 155 foot viewer height is 1.94 miles for a geometric drop, and geometric hidden is 1.49 miles. Okay, or 7,885 feet. Okay, is hidden. Okay, so distance from Point Dume, Malibu to Santa Monica shoreline is 19.21 miles. 19.21 miles minus 15.25 miles is 3.96 miles unaccounted for, because the geometric horizon is 15.25 miles. So from where Jay Tolan was, his actual horizon, if we were on a globe, going by what a globe would say, his actual horizon should have been 15.25 miles away. But Santa Monica shoreline is 19.21 miles away. And you can see here, there's Santa Monica shoreline, just over there. That's Santa Monica over here. Right? It's straight over from Malibu. Oh, here is Santa Monica. That's 19 miles away. So Santa Monica shoreline that we can absolutely see here is really there. It's all really there. And that's 4 miles further than what the horizon should be. So the horizon is what should be, or not, sorry, that's not correct. Not where it should be, but it should be if we're on a globe. Not what should be, but should be if we're on a globe. But as Nathan says, we just see it. There it is. You know, that's 19 miles away. It's 4 miles past what the horizon is supposed to be if we were living on a globe. So so that's 4 miles straight away unaccounted for. 3.96 miles unaccounted for. Occultation elevation, Los Angeles is 250 feet at 20 miles distance from photographer. So that's 20 miles away and it's 250 feet. Mountain height is 10,833 feet, minus the drop value. If you take away the drop value, it's 577 feet of the mountain should be seen. Minus the geometric hidden, there should be 2,947 feet of the mountain scene. 124 miles in meters is 199 6,558. Mountain height of 3,302 meters divided into distance of 124 miles is 60.435 times. 155 feet as meters is 47.244. 47.244 meters divided into 3,302 meters is 69.892. Point Dume's 47.244 meters treated as 1/2 of an inch makes Mount San Jacinto 24.946 inches tall. The reason I'm telling you this is I was thinking about for this presentation, I was thinking about actually doing a scale down model of it, but where at Point Dume, where Jay Tolan was standing, if that was 1/2 an inch high, right, because we're making that, let's say we treat that as 1/2 of an inch, then Mount San Jacinto would have to be almost 35 inches in height. Okay, so Mount San Jacinto would have to be almost 35 inches in height. Okay, and it would have to be it would have to be 2,112 inches away from the 1/2 inch. So basically, if you wanted to scale this down, you'd have 1/2 inch as Point Dume in Malibu, and you'd have a 35-inch tall piece as Mount San Jacinto, and it would be 2,112 inches away from you. So how would you scale that down? It's extremely difficult. To find even a car park you could do it in that would be flat enough and a 1/2 an inch high, how are you going to see 2,112 inches at that kind of an angle of view across a car park? I just knew it wasn't going to be possible, even a 35-inch high piece. So that'll tell you how crazy the distances and sizes are. The distances and the height, it's crazy, the distance between Jay Tolan and Mount San Jacinto. It's a crazy distance. I don't think people, just if anyone wants to look through that, just how to scale it down and try it, best of luck. But I don't think it's doable. So to do a scale down model of this observation, I'm going to skip through this because this is basically me talking about what I just talked about. The driving distance is 142.2 land miles. Don't mind all that. I'm going to go past all that because I've talked about that. That's just about the horizon. I'm going to go past all that because I want to keep this moving. Okay, all that stuff I've talked about anyway, or I've talked about most of it. Just the length of time we would spend in a car going there and the horizon where it should have been, if we were on a globe, as opposed to where it actually is, which is way past. We can't see where the horizon is because we can see as far as Mount San Jacinto. So where is the horizon? I can't see any horizon in the photograph. There isn't one there, because it is actually so far away. Now, these are just some photographs that from Jay Tolan himself. This is just some compression he showed that was happening. This is 300 feet here between these two here, and 600 feet between these two peaks here, and this is 2,800 feet. So he's just showing the compression that happened with the photograph. There are 3 points of compression, big compression that happened right there. Like that's supposed to be 600 feet right there. He says, and he was showing it does seem to be very compressed in those 3 places, as what happens with distance. But now I'm going to show you something else. Okay, this is right. You probably can't see this. It says 244.59. You'll be able to see if you can zoom in. I'll see if I can zoom in a bit. I can't zoom in here. It's 200. Google is putting it as from Malibu to Mount San Jacinto. Mount San Jacinto here. Google Maps are putting it as a distance of 244.59 miles, right? And that doesn't seem to make any sense. But I'm going to show you something now that's going to be a bit strange. If you can see it, this is the distance that the photograph was taken across here, and that's the distance across the United States. So is this 124 miles? Because if that's the whole of the United States, it does appear to be more realistic if it was 244 miles. Now I know people can argue with that, but if you look at the distance across the United States, that's like 3,000 miles across or something like that. Is this 124 miles? I don't know if that cuts it as 124 miles. That looks longer than 124 miles, and that's the exact same as this. I just zoomed out. Exact same as that, just zoomed out. So Google Maps are saying it's 244 miles. So I don't know. So there is the distance, 19.21 miles to Santa Monica. There it is. The distance to Santa Monica shoreline, 19.21 miles, just to prove it. Now I'm going to come down here. This is going to be important. This is a changing photograph. I got this from Metabunk. They were trying to debunk the whole thing in Metabunk. And it'll change. And what they're doing is they're showing a photograph in the background. If you take a look at this now, there's a photograph in the background and taken from a different angle, a different place or something of Mount San Jacinto. And what they're doing is they're trying to make it out as if only the very top part of this is what Jay Tolan got. So is he trying to say that he only got the very top little edge of the mountain? But if you look here, I'm going to put my cursor here and watch for the peak when they change. When this photograph changes, watch for the peak. That should be there. See, it's over here. So they actually made, in Metabunk, whoever did this, they actually made the Jay Tolan, the part of Mount San Jacinto Jay Tolan can see, they actually shrunk it up and made it smaller than it should be to fit onto that. That's what they did, which is absolutely totally shocking, right? This part here is actually over here. There's, and this part here is actually, this part here is actually over here. They actually, they actually did that. They actually, this part here should be, they have it over here. They actually made it smaller to try and belittle the photograph. And I think that's pathetic. I think that's absolutely pathetic. They literally did straight out dishonesty. It's pathetic. So here you can see again, they're doing the same thing, but this part here is this part over here. And for this mountain, this peak here is actually over here in this photograph. But they're after putting this Mount San Jacinto onto it, that from Jay Tolan's photograph, and making it, shrinking it, making it smaller, and just trying to fit it in here with the edge. But this part is that part. So I've done it myself, where I've matched up both of these, right? This part here is not visual in this photograph, and this part here is that part here. This peak here is this peak here, right? So this is proof that they have not done it correctly, and even this is stretched out more than what they had. So I come down here. This is one I put together. So now I've made them more equal in size, and now you can see that this is the bottom of the mountain, this is the top of the mountain, and this is Jay Tolan, the part Jay Tolan could see. So there's a lot, Jay Tolan could see a lot more here than what they were trying to show he could see up there. He could see half of the mountain. And you have to, and as I explained, you have to take angular size change and visual occultation into it, as Los Angeles was occulting him by 100 feet, right? And he's a 2-hour drive away from the mountain. This is it. He was seeing half of the mountain, but it's occulted in the distance. That's all it was. It's occulted by Los Angeles, and it starts shrinking in the distance. But when you match up the mountain correctly, right, to the bottom, the top of the mountain, to the bottom of the mountain, not like they did on Metabunk, not like those dishonest types did on Metabunk. When you do it correctly, like I did here, and I made a point of making it as equal as I could. This is as equal as possible. This part here is that part down there. There's the proof of it. This part here is that part down there. They are totally dishonest. What they did, totally dishonest. So this is he's actually seen half of the mountain. The rest of it is occulted, and this, for the Globe side to do that, anyone who joined in with that, you should be ashamed of yourself. You should be totally ashamed, because this is honest. What G did was not honest. So there is the mountain again, and here is the same photo again underneath it, showing. I've matched them up. They're top. And Jay Tolan's photograph, and it's only this part here that's occulted, and this is taken from a different angle. I don't know where this is taken from. It might be taken from the other side of it, because it's obviously not taken from Malibu. It's not taken as from far away. Because where's Los Angeles? Where's Malibu? Where's Malibu? Where's Santa Monica? So this must be taken from the other side of the mountain or something, or I don't know where this is taken from. But it's definitely closer. It's probably much closer from the looks of it. That's probably Los Angeles is behind this person, somewhere behind this person. So I'll just show here. Again, I have some pointers into the exactly where it all fits. So I'm not going to keep going with that. But this is it. This is the bit they were saying that all Jay Tolan saw. This little tiny sliver at the top. What dishonesty. What absolute rubbish. This is the bit they were trying to say. What about this part over here? And this part over here? Because you can see all that. And this part here, this part here was in his photograph. You know, what about all those parts? This little sliver at the top, this is what they're trying to say, is all you can see. This is what they're at. The dishonesty of it. Unbelievable. You know, this is the part, look there, I have it there in red. This is the part they're trying to say is all you can see. You know, what about all this? You know, what about all that? What about Los Angeles being in the way? Los Angeles, you know, 100 feet above them, you know. So, this is the measurement of 15.24 miles. This is where the horizon should have started if we were on a globe. Should have started if we were on a globe, but we're obviously not, you know. Oh, I'm not going to go into that. That's just about Google Maps and the distance, and this being the 124 miles, and Google Maps calling it 244. So I don't know if you look at the full distance across America, maybe it is further, you know. But even 124 is phenomenal. What's the distance here? Yeah, 2,239 miles straight across America. 2,239 miles according to Google Maps, and it's 244 miles to from Malibu to Mount San Jacinto. Okay, I'm going to keep on going because there's more stuff here and I just don't have time to get into it. So if anyone wants to look back on it, they're totally welcome. Now, right, AngularSize, right, here is just blocks. All these blocks are all half-inch height. Right, I've used them in other things I've done, little silly scale down models I've done of people's photographs and stuff like that. This in the background, you can see that the bottom of that is starting to disappear. Now that is basically the diffraction limit, because with the optics I'm using, which is just an iPhone 5 camera, it's starting to amalgamate at the bottom. So that's the diffraction limit starting to go there. But more importantly is these two here. I have zoomed a bit to this one. This one is not close. I'm back a bit from this. I've zoomed in a bit. Okay, and there is the top of this is visually higher than the this block here, but the two of them are exactly the same size blocks. There's no difference in their size, right? About the top of this block here is about the second or third block at the back. If you use a straight line, and even at that, I dipped down the line slightly. But in reality, they're actually the same height. But it's angular size change. It's the angular size change, and I zoomed to this because I remember Miles Davis said that zooming and being close are two completely different things. No, they're not. There I am, zoomed. If I was close, it would be the same exact thing. There you go. That's angular size change. You know, something that he needs to learn about. You know, there is the same block, but yet this one at the top is way over it. But it's not really. It only looks that way. Same again here. Same photograph, more or less. More or less same photograph. Some of them are doubled up. Now, here is a bunch of condiments in jars I've used on a floor. This one with the black here. This is the biggest one. These two orange ones, remember of those. The one with the black top here is the biggest one. The red one here is the second biggest. And this jar of olives. Remember this jar of olives. That's the third biggest one. Now, I've just laid them out. I'm not going to go through every photograph. But there's a couple of choice photographs I want to go through. Just showing angular size change. There you go. I have my camera at different distances and different heights, and those two are the same. These orange ones are the same size, but yet in the distance, this one is tiny, and the bottom of it is starting to amalgamate into the floor. Okay, keep on going. Right, there's a closer view of it. The bottom of it is starting to go into the floor because the camera is not good enough to see it. They basically can't decipher it. You can see how the bottom of that is disappearing into the floor. It should look like this with the glass at the bottom. And these jar of olives, which are bigger by an inch or inch and a half than this, is obviously smaller in the background, but that's just angular size change. But the globe side, the argument would call that going over the curve. You know, there it is again, closer again, and you can still see. Look, it's disappearing. You know, the bottom is disappearing. But there's just a few choice photographs I really want to. There's this same thing again. I'm just going to keep on going. Anyone wants to look at these, they're welcome to do it. The diffraction limit is happening at the bottom of both of those here. Right. Here, the jar of olives is bigger than the red one, the thing of salt. Yet in reality, the thing of salt is bigger than the jar of olives. But it's just what you're looking at. This is occulted by that. You know, if I wanted to see that, I have to basically, if I wanted to see that at the background, I'd have to raise my camera. And if my camera height wasn't as high as this, I'd have to tilt my camera up to see the top of that red one. You know, but I'll keep on going here. Sorry, there's a few missing. Right, there, the orange one here is higher. It appears to be higher than the orange one at the back, but it's not really. The black one at the back, which is way higher than the rest of them, is only barely as high as the red one, you know, just due to angular size change. Right, there we are again, same kind of thing happening, just moving the camera around closer, further, and up and down in angle. But there's a couple of one. Now this is an interesting one. You can see these red rings, red off of milk rings, off of a milk, these little plastic rings. I have them, as they go further away, you can see are starting to disappear. The bottom of these two jars start to amalgamate with the floor, and this red ring here is completely different from this one here. It's starting to just melt into the floor. If that wasn't as bright a color, you wouldn't see it. You know, so there is a great example of the diffraction limit, right? Due to optics. I'm using an iPhone 5 camera, and that's what you got. Maybe with a better camera, you'd see it clear, right? But you won't see it clear with the iPhone 5 camera. You know, so it's down to the optics that you're looking at things with, okay? And here at the bottom of those are melting into the floor. So I keep on going, right? Sorry. Yeah, that's just showing the two of them standing side by side, and the red one here, how much bigger it is than the salt is than these two. Now, this is just showing the height difference over that, and this small little height difference between the one with the black top at the back and the orange one here. There's only a small little bit, but you know, in reality, that's nearly double the height. But I'm going to keep on going here. I'm going to keep on going. That's more diffraction limit, because I want to get to important stuff. Now, this jar of olives. This is an interesting. This is the best ones I've got, because I just had used two, just the orange one and the jar of olives. And watch what happens with the jar of olives. Right, in the background it's higher, right, at the moment, but watch when I change things around. Right, change. I move myself to a different angle of view, same camera height, and the jar of olives is not so high in the background. Okay, if I go down, now this is just me closer to the floor. The jar of olives seems to have sunk into the floor like it's gone over the curve, but it didn't. The bottom of the jar is gone. It's like as if there's a curve on the floor and it's gone over a curve, but it didn't go over anything, because I just dropped my angle of view. My angle of view got tighter, so the jar of olives disappeared at the bottom. You know, it shrank. It's shrinking into nothing. That's what it basically happens. It's basically heading for on the horizon, and that's what happens. You know, this is higher than that. The jar of olives is disappearing into the floor. Sorry. And there it is again. The jar of olives, the bottom is not as, or this one is not as severe. The jar, I'm up a bit higher with the camera. Jar of olives is the bottom of it. You can't decipher properly from the floor. Okay. Now, this one, right? It's occulted by the orange one, and I go down. Sorry, that one. No, and I keep on going. There's a couple of good ones. This one is good. You can't really see. You can see that the bottom of the jar of olives seems to be disappearing behind something, but it's not. The floor is flat. You know, it's just where my camera is and what's occulting it. You know, and its distance is starting to shrink in the distance. That's all it is. Let me see. I'm going to keep on going. The same is happening here up to a point, and there's the two side by side. So what I'm going to do now is, just before I go further on, I'll go past that part and past this part, right? Before on, I'm just going to show this, right? There's the first photograph, right? There's the second one, just changing my camera height. Third one, you can see the jar of olives seems to be, the bottom of it seems to be disappearing into the floor. There they are together, okay? And this one, right? This is a great photo. I'll just go to this one here. From there, changing my position and then changing my camera height. Look what happened to the jar of olives. It's like as if they went over the curve, but they didn't. They didn't go over the curve. They're still there. And they're actually physically bigger than this, but it's just my angle and my angle of view. I just got closer to the floor, and so the bottom of the jar of olives seems to have disappeared. But it didn't. It seems to be gone over the curve, but it didn't go over any curve, because there it is. I just changed. Kept them in the same position. I just changed where my camera was. Look at that for a difference. It's like it's gone over the curve, but it didn't. Now, looming. There's actual looming. This is actual looming, what you're seeing here, right? This is important. You're seeing actual looming here. Okay? That's what real looming looks like. There's more looming. Okay? More looming. So for people who want to know what looming is, this is not looming. This is an effect on the water. It makes it look like the boat is floating in the air. It's not. It's the effect is on the water. The horizon is actually here, but the boat looks like it's floating, but it's not. The water is actually under the boat. Sorry. Same happened here. The water is actually under the boat, but it looks like the boat is floating, but is floating in the air. It's not. It's still floating on the water. It's that due to an effect of the water, the horizon is actually out here, out past the boat, but we just can't see it. There's some. This is what can happen. Look at this building. This is what can happen with photography or with weather. Look at the stretching that's going on here. It's that they're stretching up in the air from its normal position, and now it's shrunk down to the bottom. So this is what can happen. This is what can happen with compression. Okay, you can stretch and compress, right? In your field of view. A road, same kind of thing happens as what happens on the water. The road seems to have disappeared, but it didn't. I'm not going to go into this. I was going to go talking about this thing with shoaling and stuff like that, but I'm not going to go into that because I just threw that in at the end, and it's more Ranty's thing than mine. But I was going to talk about the distances between these and how it's impossible for that to be that far gone behind those at that distance. But I'm not going to go into all that now. Same with there. So there's a stretching on the stretching here on the containers on that ship. I'm not going to go into all that. That was more stuff. This is about angular size change again. I'm not going to go into that. I'm going to keep on going. And same again here, angular size change. But now this one, right? This is one of the best angular size change examples ever. This is Miles Davis's photograph from Traprain Low to the Carnock Hill. Right, with the bridge stanchion here, that's only about half the height of Carnock Hill in the way. But Miles Davis is about 25 miles or something like that from the bridge, and then the bridge is about another 24, 25 miles from the hills at the back. Right, and as I showed earlier, with all those photographs, right, what angular size can do, right, how angular size can change our view. Now, this is not going over the curve, right? Miles doesn't seem to understand that. Right, or doesn't want to understand that. This is not going over the curve. This has just gotten smaller with distance. And I told Miles that within 20 minutes of him posting it, this original photograph, I had never seen him before. I told him, I said, Miles, things get smaller with distance. No way would he have it. That's exactly what I told him back in 2016 or whatever it was. Right, he didn't want to hear it. Things get smaller with distance, and that's what happens. And I can prove it with little things on a table, you know, or I can prove it with big things. It doesn't matter. This is the proof. You're actually showing this is perfect angular size change, you know, and occultation up to a point, but perfect angular size change more than anything else. But he didn't want to accept it. But unfortunately, it's the truth. It's angular size change, not going over any curve. I'm not going to go into this. This is just stuff I'm going to talk about. Angular size change of like 443 kilometers away, Pic Gaspard. This famous photograph, which has been beaten now. I think there's another one now that has beaten it for long distance photography. But look how small that looks. It's tiny, yet it's bigger than where the photographer is in height. But it's tiny. But it's not going over the curve. It's just gotten small with distance. Simple stuff. Now, this is the part I want to finish on. Ranty's 1 foot observation. The coup de grace. Okay, from a 1 foot camera height, Ranty was able to see Barrow Town Hall 18 miles away, even though his camera's angle of view was being occulted by a sand dune of 35 feet in height at a distance of 13 miles. Okay, this is Barrow Town Hall here. Barrow Town Hall height is 50 metres. Okay, elevation 222 feet, distance from camera 18 miles. A 1 foot observation height at 18 miles away supposedly has an obstructed view of 187 feet, 187.66 feet, without 7.6 refraction, 7/6 refraction added, or 158.97 feet with 7.6 refraction added. So only 63 feet should supposedly be visible above a horizon edge if 7.6 refraction is added, and only 34.34 feet should be supposedly be visible above a horizon edge if 7.6 refraction is not added. So just over 100 feet of Barrow Town Hall should be hidden behind the horizon edge, going by these calculations. Also, the horizon would be between 1.22 and 1.32 miles away from the camera lens if we lived on a globe. So basically what I'm saying there is at 1 foot camera height, there should be an horizon at 1.22, between 1.22 and 1.32 miles away. Okay, yet Ranty is seeing 18 miles, right, and he's seeing this building 18 miles away. Now, there should be, if we're on a globe, there would be 63 feet, 34.34 feet. If you don't add in refraction, there should only be 34 or 35 feet should be visible above an horizon edge. Okay, if you add in refraction, it should be 63 feet. If you add in refraction, as in standard refraction based on curve calculators, not on real refraction, but what they would call standard refraction. Right? If you added that in, there should be 63 feet. Now, this is not what we see. Right? Sorry. This is 1 foot camera height. This is Ranty looking across the way. Now, you'll notice some of these things here, up here. Right? This is actually Looming up here, what he's showing here. So he's seeing the town hall area over here. Okay, this is the town hall here, over here. He's seeing this 35-foot dune here, and above the town hall over here, you have Looming. Okay, so how could all this here be loomed up, right, at a 1 foot camera height when Looming is going on above it? You can't get a mirage from a mirage. This can't be a mirage because this is a mirage up above it. So if this is a mirage, this can't be a mirage. But we know this is a mirage because it's inverted. Okay, this is loomed up above it and it's inverted. So this here has to be real. So Ranty is really seeing this shoreline here and this 35-foot sand dune here, and 13 miles away, and the Barrow Town Hall here 18 miles away from a 1 foot camera height. This is really happening. So because there is Looming here above his observation, then that you can't get mirage from a mirage. You can't get Looming from a mirage or Looming from Looming. That's it. This is really here. That's the proof of it in the story. There's no getting around that. Nobody can argue with that. Nobody. I put a line here to show the point where the inversion starts. Above this little yellow line is where the Looming starts. Above it is what we see. So this is, and below this yellow line is really there. There's Ranty's camera, 1 foot height. This is really there. And this here is the 35-foot high sand dune, which is occulting Ranty by 34 feet. Okay, I'm not going to go into all the calculations of it there. Sorry. So this is it, same again, right, just a different angle. Same again, 1 foot camera height. There it is. Right, he's seeing that far, 18 miles away here and 13 miles away here. He's seeing that far. This is all loomed up over here, right, from a 1 foot camera height. He's seeing that far. His horizon should be 1.22 miles away. There he is again, zoomed into here, 1 foot camera height. This is stretched here. This is all stretching here. That happens, but he's still seeing everything from the bottom up. So how can you have Looming creating Looming? You can't. Doesn't happen. It's impossible. You know. There's the very bottom. I did a little yellow line showing where the camera lens would be. That's the height of his camera lens. Right, he's seeing this. This is about 13, 14 miles away. Not Barrow Town Hall is 18 miles away. Okay. Now, the yellow line shows where the Looming mirage starts, and the red line shows where the horizon should be if we are to go by globe mathematics. So if we were on a globe, that's where the horizon would be. That's as much above you. So basically, between the yellow and red line is all you should be seeing if you're on a globe, right? That's all you should be seeing at that distance. But at one point, right? So that horizon here should be 1.22 miles away from you, and all you should see from a 1 foot camera height is just this part of the building here. Everything above the yellow line is all Looming. So this is really there because that's all Looming. You can't get Looming from Looming. Can't get Mirage from a Mirage. You're going to get Mirage from something real. And we know this is the Mirage because it's upside down. Right? This is not Barrow up here. This is Barrow down here. 18 miles away. Just to finish, just take notice of these guys in the boat and the ship in the background. Take notice of this, okay? I'm going to go down further. There is the bottom of their boat. Now, they're about 7 miles away from Ranty. There's the bottom of their boat. Okay, that is their boat on the water, the bottom of it. That's it floating. That's what those boats float like. They're like a catamaran. I know what they float like. I've been out in the sea a lot. That's what they float like. That is the bottom of their boat. Okay, here it is again, the bottom of their boat. They're about 7 miles away from Ranty. Okay, there's the bottom of the boat again. All right, here. Right, very last photograph. The little dot there. This is from 0051 on Randy's 1 foot observation on his video, right? When he zoomed in, right? Well, this is when he zooms out, right? 0022, about 30 seconds later or something. He zooms out. That little tiny white dot there, right, is, I'll just show you, it's that part of the ship. That's what he's seeing with that tiny white dot. So that's how far away he is. That tiny white dot is the top of that ship. He's 1 foot off the water here. So he's seen all that far, all the way over, with Looming in there and all, above the thing he's actually seen at 1 foot camera height. That can't be argued with. Anyone who denies that or tries to avoid that is only lying to themselves. Can't be argued with. 1 foot camera height, 18 miles away. There's the top of that ship. It's only a little tiny dot from 1 foot camera height. But yet, he can see the ship. Sorry. You can see the ship right there. And he can zoom all the way to Barrow Town Hall and see all that. And the Looming above it. So, that's the end of that. I had to cut out a lot of it. There was some more parts I wanted to go into, but I had to cut out a lot of it. So, that's the end of that, Randy, if you're still there.
Yeah, I'm still here. I've got a bit of an echo coming through.
Okay. Do you want me to unshare the screen?
Yeah.
1 second now. Where are we going to? Skype. Okay. Stop sharing.
Now, hopefully. I'm still getting a bit of feedback. Have you got the watch page open?
Seeing it, but I have it on mute. Have it on mute. Are you still getting feedback from me? Do you want me to hang up and ring back?
It's when I speak, so it's you're getting back what I can hear. So have you got the volume up?
No, I have it on mute. I 1 second now. I only have my own volume up. I have the watch page on mute.
Okay. No, I mean, have you got your earphones in?
I'm talking through the laptop.
Ah, right. Okay. So that's probably why we're getting a bit of echo.
Yeah, and I only have the. Do you want me to hang up and ring back, or something like that?
I'm not sure that would help.
Yeah, and you're hearing yourself when you're speaking to me.
Yeah, I'm hearing it, so I don't know if the audience is. Oh, there we go. It seems to have worked out a little bit there.
Yeah, because I have the watch page on mute, so I don't know what was.
Okay, so what I'm going to do now is I'm going to pop out the chat. So I'm going to take some questions from the audience. So here we go. I shall wait and see what people have got to ask you. And sorry, go on.
I'm just saying I don't know if there'll be a whole lot of questions on it.
Right, well, you never know. Let's see what they've got, because I know Nathan is starting in 20 minutes, so it gives us 20 minutes. So 20 minutes for people to ask you anything they like on that presentation. Hey, nice stuff with the that set of images that you put up as well. Actually, that was pretty cool.
Oh, that 1 foot of camera, 1 foot observation.
Yeah, some guy did an observation. I don't know who it was, but it seemed pretty good evidence,
Well, it looked like the best evidence I've seen. Whoever he is.
Okay, so
having that in.
So first question is from the Rumpus, Brian.
Oh. Yeah.
How do you manage to be so stupid?
I don't know what way to answer that. A lot of practice, Rumpus. A lot of practice, by. That's all I can say to that, you know. Because that goes what I'm after showing there goes completely against his 900-page presentation.
And
yeah. Go on.
So obviously you've had a bit of back and forth with Rumpus. So I suppose that's why he's a bit tetchy with you.
I know he's going to do that. He's never going to, he's not going to go, wow, that was great, I really learned a lot. He's never going to say that. Not after he has a 900-page presentation ready to go, so totally against what I'm after putting forward there and what you put forward. Like, so he's not gonna give me a pat in the back.
We've got a question. Well, not a question. It's it's from Paige, actually. I'm just going to tell you what she said. She says, "Will Brian do the eulogy at my funeral?"
The eulogy, Jesus.
I know they're taking digs at you tonight, but and Paige is on our side too, you know. From Ian Adams, great work, Brian. So good stuff.
Thank
you.
Stuff.
Come on, surely there's some globs in here that have got some issues with the presentation that Brian's just put together here. You know, this is your chance to challenge him. This is your chance to win. You know, let's see what you can bring.
But the thing about it is that everything I talked about, I showed physical demonstrations of. So it's kind of hard to argue with it. You know, although they may not want to believe it, I may not go along with what they would prefer. I showed angular size change. I showed visual occultation. I showed the diffraction limit. You know, things like that. So, like that jar of olives, like all I did was drop the camera height down lower, and the jar of olives seemed to have gone behind the curve. That was just down to the angle of view.
That was similar to what Nathan did, isn't it, with his book?
Yeah, same thing.
So Nathan says that his show started in a couple of minutes, but nobody really wants to go there. It's only the pre-show, and it's pretty dull to start with. You don't have many people in there, so I would hang around here for a bit. You know, let's ask a few more questions till midnight. Right.
Rumpus, I don't understand the curvature calcs and whatever else. You don't realise that Ranty was not at 6 inches to 1 foot. He was 1 foot. Let's just say Ranty was at 1.5 foot. No, not that he was. It wouldn't matter. I shouldn't be seeing all that, Rumpus. You know, shouldn't be seeing it. Full stop. Like, you know, there's no way around it. The looming was above what Ranty was looking at. You could see the water lapping just at the cameras, just at the edge of the camera almost. You know what I mean? How low does he? You know what I mean? It's like you can't have looming from looming. We were seeing every part of the thing 18 miles away, and every part of the shoreline 13 miles away, with looming above it. So there's no way out of that. It's a kill, you know. So I don't need to understand. I do understand the curve calculators. They're presupposition machines. That's all they are, you know. They're like, what should be is this, or what should be is that. But then that's not reality, you know. Go on, sorry, Randy.
So Mason B says he missed most of the show, but he has a question. How many globies did you trigger today?
I don't know. I don't know. Like, they don't really want to hear that. They don't want to learn. They don't want to accept that. Like, angular size change is the reason why is a big reason why things seem to have gone behind what they think behind the curve. It's just angular size change, visual occultation, and diffraction limit. You know, if I said what I said. I showed visual. You know, I showed demonstration of it. You know. I even showed a demonstration with Miles Davis' photograph. You know, like that was great angular size change. You know, perfect. You know, but he doesn't want to accept that. So,
from Sharpie Quartz, more of a statement really, says ground distortions due to humanity too. So I'm going to say that that's ground distortions due to humidity as well. So yeah, I mean that's what we tend to see. You know, if you get this evaporation happening over any object, so it could be over the sands, it could be over grass, it could be over water, you'll get this evaporation happening, and that always happens right at the ground level. So you are going to get a lot more liquid in the air at that sort of those sort of heights.
Yeah, I mean, you can't not, like, you can't not. I mean, but look, I don't see how anyone can argue 1 foot camera height, 18 miles away, the looming is above it. That's the end of that. You know, you can definitely say that that part of the world is 100% flat. You know?
Well, what I'm finding here, to be honest, is I'm finding a correlation between the depth of the water over those distances, the span of the depth over those distances, as opposed to in other places where you get these greater depths, these drop-offs. So if we look across shallow bays that have a long depth of a long constant depth of, say, between, let's just give an arbitrary number here of 1 meter and 15 meters, and you're looking across 18 miles of that sort of depth, it's normally pretty good observational stuff, especially, you know, like with Red Pill Philosophy when he did his observation, where I do my observations. I've also found some areas where when I go into those areas, I've noticed that the terrain, the topography of the land underneath the water is around about a 40-meter depth, and across those little areas there, I get obstruction. But then I go 100 meters further away, and it takes me away from those trenches, and I'm looking across this terrain that's all flat and level underneath the water, and you see flat again. So I'm definitely seeing a correlation with that.
Well, it makes total sense because water is bonded. It has bonded molecules. Water has bonded molecules. That's how we have a wave. A wave wouldn't be possible if it wasn't for bonded molecules. So water will flow over something. You know what I mean? And it will swell over something. You know what I mean? But it will swell over with an attempt to flatten out again. It's always trying to flatten out, but there's always stuff stopping it from being flat. Do you know that kind of way? But because it has bonded molecules, you know, it will flow over. Anything that's there will swell up. So as you're saying, if there's a 40-foot drop, you will see a swell right there. You know, if the water is moving, especially if the tide is coming in. You know the way the kind of big tides that we'd have here and you'd have over across the water. There'd be big tides. The tide would go way out and come way in. You know, there'd be a big huge swell of water coming in. You know, on the incoming tide. You're going to have that. Now, even I told you about that sandbar 200 meters off of the beach in that the lagoon I was telling you about the other day. I mean, that happens there. That shoaling basically happens there. Basically because of the sandbar, you know?
Yeah, and like I say, I mean, it's something to look into. I think what we're going to find when we look into this now, this shoaling effect is going to have a massive effect for angular size change, essentially, and also, you know, its proximity to the shoreline. Obviously, you've got your distance that you can only see for a certain length of distance anyway. And then obviously, you know, when you do see these great shore-to-shore observations, normally they're over a topography of the land that's very flat underneath the water, you know, so there's no real drop-offs or anything like that. So, and that kind of just disproves the idea that water's curving to 8 inches per mile squared, as it has to, if you believe in gravity, that gravity is curving that water, being a liquid, it has to conform to 8 inches per mile squared. It can't fight against gravity. If it did, we'd be all flung into space, you know, in an instant, you know, if gravity took a day off. So that's why you can't have flat water. Whenever we see these great drop-offs, you see boats actually hidden. I was glad that you actually got around to getting to that point, but you didn't go over it. You left that for me to talk about at some point. But
yeah, that photograph there, what's interesting about that photograph is that you have two boats in the foreground and they're like 6.5 and 7.5 miles away, and then you have another one just 2 miles behind it, and it's missing the one that's 2 miles, and you can see both of those, but the one that's 2 miles, that's at 9.5 miles, which is only 2 miles past the second boat, is 2 miles past that, and we're missing like about 60 foot.
Well, what's happening there is you've got the boat itself, because boats float, obviously. So the boat is sitting on the swell, on the top of that shoaling effect. It's literally on the top of that, and then the boat that's 2 miles further away is beyond that shoaling zone. So the water settles down again, so it's not as high. So in appearance, it's beyond that hump. It's beyond that hump that's being caused by the shoaling effect. Whereas the boat, the big boat that's in focus and fully visible, you know, to the hull, you're actually seeing because it's sitting and floating on the shoaling, and then behind that, when the water drops and levels off again, you're actually seeing the boat that's a few miles further behind that, but then has got like 40 or 50 feet missing of it. And like you say, that cannot happen on a globe. That can't happen on a globe because you can't get that sort of additional curvature over that distance over just 3 miles. It's impossible, like you say. So you should get maybe 6 feet or something like that, 7 feet.
Yeah, exactly. There's literally about 2 miles between the second boat and the one that was mostly hidden, the third boat. There was literally 2 miles or something between them, like 7.7 miles and 9.8 miles or something. And there's like basically 2 miles, and within 2 miles is only 2 miles is 32 inches. So yet they're missing about 50 foot of the boat. You know, it's just not possible. You know, between those two. You know. There's also a lot of time people are taking these observations in shipping lanes, and often shipping lanes are going to be where there's going to be a big depth. You know, they need a big depth, but there's always going to be a shore. So you're going to have shoaling in that area because it's perfect for the ships. You know, they need depth. But on top of that, the shipping lanes are going to, because they're constantly big ships moving container ships and that, you're going to constantly have you're going to onshore waves and onshore swells coming from the fact that it's a shipping lane, because they're constantly displacing the water. You know, so that 2 foot swell or 4 foot swell that's created by that ship that's 9 miles away could be enough to block half the boat. It depends on your position, how far away you are, or whatever. You know, that kind of way, or what height your camera's at. You know.
Right. I've been looking for any kind of questions from the chat, but it just seems like they're arguing between one another. They've got these personal beefs that they're still going on about right now, so we're not really going to get anything more done this evening. So I want to thank you for actually coming along and presenting your case for all the stuff that you've been working hard over the Christmas. I do appreciate all the work that you put in. And if you ever get the opportunity to revisit some of the stuff you skipped over, I'll gladly do an offline presentation and upload it as a standalone video if you want. Direct people over to your channel, which is called Brian's Logic.
Yep, thank you. Thanks
a lot.
Thanks for appreciate it.
No worries. So Nathan's gone live right now. I want to thank him because he actually gave me a super chat earlier. Thank you for the £1.99, Nathan. I'll buy myself a chocolate bar as I promised you I would. And everyone else that's been in, we've had over 100 watching, which is pretty cool, seeing as I've just started these shows off again. Again, like I say, I am looking for new people to come along and do more presentations. You know, you'll get a free reign just like this to make your case. If you're a glober, concaver, flat earther, it doesn't really matter. Just come along, put your presentation, we'll get the audience involved afterwards, and that will be it. There'll be no commotion, you won't get any kind of argument from me. It's basically giving you the platform to actually go ahead and present your argument, present your case. In the meantime, that'll do for now. I'm not sure when I'm going live again. It probably will be again this week because I've actually got the bug back again now. So I'll be back again this week. If you want to support me, if you want to support the show and you want to support the research that I'm doing, head on over to Patreon and look under Ranty Flat Earth. You'll find me there, all different tiers of support that you can do, and I really would appreciate it actually, because I told everybody to unsubscribe from my Patreon a few months ago because I wouldn't be very active for a while, and so they duly did. And now that I'm actually starting off again and getting things up and running again, and I've been back on the scene for the past 6 or 8 weeks, it'd be nice to get some support back on there. So if you can do that, I really would appreciate it. In the meantime, I do believe one last thing's in order, and that's to thank Sleeping Warrior for winning his award. He actually wanted to win the award, the Dumb Fucker of the Year award. He actually wanted to win that and told all his subscribers to go and support him and click the links. So I'm glad that he did that, because he essentially took away their victory by doing so, because he actually produced it himself, essentially. In the meantime, that'll do for now, guys. Heading over to Nathan's, and I'll see you all in the next one.